Oops. Okay, wat staan we in de les? We waren de laatste keer bezig met beschrijving van de faseovergangen voor Friedmans leer van Zelfspraak van radicaal van M, zodanig je voor alle gebogen als alle unabhängig van M geldt, aantal elementen in de I grenzt door Stefanie. Als het geval is, dan en dit is interbedden. En dan heb ik gekeken. Er was deze kritische constante. Dit was de constante alpha. Constante van Otter. En is ook mathematisch. En die heeft daar berekend boven 10. Daar is dat 10. En heeft. En dat is asymptotisch gelijk aan tot in 3 over 2 keer een constante. Oké. Nee, hoe doet men dat? Door opschrijven van de genererende reeks voor de Tn. Dan moet men kijken wat is de natuur daarvan. En 3 over 2 duidt erop dat dat een speciale singulariteit is. En als men zeg maar een wortelfunctie heeft, dan drukt men deze termen op. En het is ook zo, de genererende reeks heeft zogenoemde wortelsingulariteit en heeft ermee te maken. Maar goed, moeten we allemaal niet weten. We moeten gewoon weten, Tn is in principe zo goed als alpha tot de einde. En alpha is 4,95, etc. Dan heb ik gezegd, een kritische constante C is 1 gedeeld door log 2. 1 gedeeld. Wat is het nu? Nee. 1 gedeeld door log 2 van alpha. En dan heb ik wat gezegd? Stelling was theorem. The theorem was first, if a rational number A is less than or equal to C, then a simple theory PA proves that FR is R times R divided. Then PA does prove FK3 R. And second theorem is if R is bigger than C, then PA does not prove it. And the first one was easy in the sense we just did some combinatorial argument using this estimate. So how did we do so? Well, we started with some k, then we put a double exponential function of k for m, and then we looked at a finite sequence, and then by counting argument, if the sequence was long enough, then 2 elements have to be the same. If they are the same, one is embeddable into the other. Sort of trivial counting. And then we started to consider this one. And this was difficult. And what we did last time is we showed a lemma. Namely what? FKT R is bigger than C, then FKT R implies FKT. That is what we showed. And now the point is, Matuszek and Little showed. Okay, that's not true. FKT 4. And therefore, this is certain. Now, this is a bit cheating because we haven't seen the proof of this one. So now I will prove this one. And the proof goes like the proof over here. So what was the basic idea? We started with some sequence of trees. And then we moved it to the new sort of trees. And the new sort of trees was basically what? We took T, we took the binary length of I. Here we had special tree for degree m plus 1. And here we were counting, we took the enumeration function of a certain set m times binary log I, so 2 times binary length of I of length of I minus I. So the binary length of I is, let's say, binary log I plus 1 wrong. And what was the trick here? Here was the enumerated trees of all degree bounded by m. So at every node, maximum m direct successors. And the number of elements in this class MQ was this result of our degree of Q is bounded by m, and the number of nodes in T is bounded by 2 times line length of I. And Q was in between C and I. Now, why I'm repeating this? Because this is the basic idea in the proof. So we have start somehow with sequence, and then we produce a new sequence. The new sequence has a property that the number of nodes in BI is compressed. So here we know the number of nodes is maybe bounded by 4 times binary length of I. But in going from T to T index binary length of I, the number of nodes here is bounded by 4 times binary length, also binary length of I. So log of I, so much smaller than log of I. And here is Q times binary length of I. Q is smaller than R. So in total, we get here trees which basically have number of nodes bounded by R times binary log of I. So this is the picture of the proof. And then I basically said, what? So I was starting with giving a K. And then I want to show this one. So I take K for this one, and then make K a bit bigger, so that it fulfills some of the properties. So I'm going from such K to a K prime. Then I'm applying this one. such that if I have a sequence of trees where the number of nodes is fulfilling this property, the nodes is formed by k plus f r of I. Then I find some indices I and j such that j I3 is available to j. So for the bi's, I find these indices, and then I show if some bi is embeddable into bj, then it gives rise to an embeddability of some moment of t binary length of I into t binary length of j. The binary length of I is smaller than binary length of j. That is what I did last time. Now, how to think about this? The idea is basically we have here our situation. Here is 4 times binary log, and here is r times binary log. And from the unprobability here, we move somehow. There's sort of operator moving sequences here and the sequences here. And the Z operator, and this is somehow what can be considered as in physics, you could say this is a renormalization operator. So you press down until you can no longer press it down. And the point is, once you have applied this, you get the bound FR. Of course, you can apply this procedure again, but you will not be able to press down FR below the C. So you can only stay above C, whatever you do. So in some sense, it means you reach some sort of fixed point. Now the next step is we go a bit higher over here and press it down to this situation. We go further. At some moment, the complexity will be so big that it's easy to show the independence. Okay, that's a plan. And yeah, so the next thing is we take I is I to the 3, and then we will show what fkt f4 plus fkt function f. So what we do is we start with this assertion. Take some k, and we make k a bit bigger, and then we apply this assertion. So this means if I have a sequence where the number of nodes in the sequence is bounded by k prime plus 4 times binary length of I, then the sequence fulfills the embeddability property. Now the point is, so here the BI is basically bounded by k prime plus r times binary length. Now this was a transition from here to here. Now what I now do is I start with such a sequence of trees where I bounded by a plus I to the 3. Then from the TIs, I do the same construction, I go over to the B of I. I just use here the T's, put them in over here. It's the same stuff here, same stuff here. Here I have more flexibility, but I can just stay with the function here. Doesn't matter. So what is going to happen with the binary length of what is happening with the number of nodes here? Bounded by yeah. So Ti is this one. What is the log of I? Log of I is k plus log of I to the 3. What do I see here? I see a problem. It's not so good. Let us first take this function. Okay, anyway, so Ti has this property. Okay, then this is bounded by k plus times length of I plus some stuff 5 plus, and here comes q times I. So maybe it's bounded by yeah. Now what turns out is if you check this one, this is bounded by 1k tilde plus 4 times 1 length. Is this true? Well, this C is basically 0.63, so it's strictly smaller than 1. And R can be any number, so I take R 0.7. Then Q can be bounded by R 3 times 1 length of I plus 10 lengths, bounded by 4 times 1 length. Okay, so what is then shown? The sequence of trees Ti fulfilling this property is moved into sequence Bi fulfilling this property. So this means by Matuszek-Löbel, I can show the Friedman theorem for this linear function. And that's basically how it goes. So the next step is to take here a variant of this. What could we take? Maybe a bit more. And if of I be I to the 4, then the claim is, well, let's maybe this is prime, double prime, fkt f prime implies fkt f double prime. How does this work? Well, we start with a sequence of trees Ti. Ti this property is bounded by k plus I to the 0. Right, and then what can I say about the BIs? BIs is bounded by k plus outcomes binary links I to the 4 plus some stuff. And you see this is bounded by k tilde plus I times 3. Okay, now we have proved if f is polynomial, then we are done. Next step is we take the function f of I. Let us check what's going to happen if I have here an exponential function. What I want to have is fkt double prime plus fkt f triple prime. How does this go? Well, we start with the sequence of trees fulfilling a property like this. Now, what can I say about the corresponding BI? Bounded by k plus the binary length of I plus 5 plus 2 times binary length of I. This is bounded by 2 to the length of I is basically linear in I. So linear in I, but this is bounded by the tilde plus. So what is learned by this? There's this genuine transformation from a given sequence, trees of large complexity. I go over to a sequence of new trees of low complexity. And the trick is always I replace T of I by T of binary length of I. And this compresses complexity. So you see here, from I times 3, I can go to 4 times binary log. From I times 4, I can go to I times 3. From exponential, I can go to I to the 4th. Now, what is the next step? Take here 2 to the, let's say, I plus 1 to the 3. So we reach somehow, it's not really double exponential, but it's quite strong. What can we say? So the claim is here, kt f4 implies kt f3. What does this go? Just like this. You have here the other way around, yeah, right? Yeah. Yeah, I just want to make the f's bigger and bigger. You're right. So, but now you see here, T of I is bounded by k plus 2 to the I. What can I say about the D of I? Is bounded by k plus 2 to the length of I. So, got some rest. Bounded by a theta plus So trivial, right? So there's a way. The next step is you can then introduce double exponentials, reducing it to this function. And then you can treat triple exponentials. So you can go higher and higher. The only problem is at some moment you have to come up with what we learn here is you can go higher and higher, but at some moment there should be position where we stop and really have an unprobability, right? Now that's the point. Now we use what we know already. Namely, we know something about the Hydra battle. And now we apply the Hydra battle to show that for this function, FKTF becomes unprobable. So what we will show is FKT for this function implies termination of the Hydra battle. But we know termination of the Hydra battle is unprovable, and then we are done. How can we do so? Not so clear. Well, playing is now KT implies standard Hydra battle. Okay. So what? So what was it? Hydra was the statement for all K. There is an M. Yeah, it's an M. Such that we start with omega K. And we have omega K at 0. Then at 1. And we have the M. And then we hit 0. Right? So we have we start with a K, and we build an omega tower of height K, and then we step down a fundamental sequence. This takes a long time. And the time needed to reach 0 so big that it exceeds the scope of the we only show this implication, and in the lecture on proof theory, we will learn why this is actually not provable in PA, but this is a non-trivial result. Anyway, we are happy with this. So okay, so let's alpha omega K and alpha I plus 1 alpha I at argument I. Length. So then alpha I plus 1 is smaller than alpha I. Alpha I is not yet 0. If alpha I is 0, you cannot step down further. We claim that alpha yeah so it came now choose M for KT for a function. So we take K and choose M according to this statement. And now we claim this M is good to verify this property. Claim alpha M minus 1 is less than equal to alpha M. Hence, due to this property, alpha M minus 1 is equal to 0. That's nice. And now we have to make a translation between trees and ordinals. And we have to explain what is the relation between tree embeddability and ordering on ordinals. And this is a beautiful correspondence. And actually, this is also the argument how Matuszek and Löbel were proving their results. The Matuszek and Löbel were not using this impression technique. They used some different stuff. But they used the correspondence between ordinals and trees. Okay. So that the norm function, the ordinals and the mathematics we find as follows. The norm of ordinal 0 is 0. And if I have ordinal like this, and the norm form has that the property is n plus the norm of alpha 1 plus the norm of alpha n. So to put it simply, the norm of omega to the alpha plus beta, the same as 1 plus the norm of alpha plus beta. How to think about this? This is, in some sense, the length of an ordinal term. You can also consider this as n ordinal counts the number of occurrences of omega in such a normal form expression. So you see n times omega and then count the exponents. Okay. So what? Then one can show the norm of alpha I is bound by the norm of alpha times plus 1. Why is this the case? Well, basically, you have to check here's omega to the beta plus 1. And I, this is omega to the beta times I plus 1. When you check here, so the norm of this one, the norm of this one, this is what? This is 1 plus the norm of beta times I plus 1. This is bounded by the norm of the beta plus 1 times I plus 1. In case that we have this property, that the fundamental sequence is calculated for terms of the form omega to a successor, we see that this result is true. Now, for the rest, the norm as a property, it mutes the sums. This means when you write a number in this form and you calculate the corresponding norms, well, it's just sums of first terms, somewhat sort of easy verification. And of course, if you go into the exponents, the norm of omega to the alpha is just 1 plus the norm of alpha. So this is easily shown by induction on the norm of alpha. What does this mean? Well, we look at the numbers. What can we say about complexities? Well, the norm of alpha I is bounded by the norm of alpha 0 times I plus 1 factorial. Why is this the case? Well, by induction on I. If I is 0, it's fine. And the norm of alpha I plus 1 is the norm of alpha I. Using this property is bounded by the norm of alpha I times I plus 1. You plug in your induction hypothesis, bounded by the norm of alpha 0 times I to have here. Okay, here plug in the induction hypothesis. No, maybe I'm a bit overshooting. This times up. So this bounded on by the norm of alpha 0 times I plus 2 factorial. Anyway, these estimates don't matter that much. What is here the point? The point is you want to have information about the norm of alpha I. And what you see here is basically the norm of alpha I is bounded in the first term, and then the rest is some sort of double exponential. Here's a factorial, and for factorial we know I factorial is bounded by what? I divided by E I, something like this. This is bounded by 2 to 0 s. Whatever. And the point is, if you forgot your bounds on factorials, it doesn't matter. You can also work with triple exponentials here, because we have in this business of applying our renormalization procedure, you can produce any tower of exponentials. Now, the point here is, this is bounded by, when alpha 0 is omega k, this is k times 2 to the, now I have I plus 1, I plus 2 to the square. Not too bad. Now, we have to be a bit more careful, namely, I was a bit sloppy, because here is times, not plus. And here we have k plus. Now we have to make times into a plus. How can we do so? Well, this is bounded by a times b is bounded by a squared plus b squared in natural numbers. So we bound this then by a squared plus this number square. Right. Okay. So then what I have to do is So choose M for this function and make it a square. So the point is, I start with this one from the sequence. I want to show what defines this M. Now I have this available, so I can choose for any k and m, and I don't take the original k, and I take here now k squared. And so m is now depending on k squared. Why is this important? Because then I have this one. And okay, basically what I need is this one by the square plus 2 to the I plus 1 to the 3. Okay, that's one. Okay. Now, still not clear what's going to happen. The only thing what we have now seen is we form the sequence of ordinals such that the norm, the limits of the sequence, is bounded by such a term. Right. Now comes the transition. Define by magic. Function t from ordinals into trees. And this function t will be a bijection. T of 0 is a tree consisting of one root. And t of omega to the alpha 1 plus omega to the alpha n. This were by recursion. We assume we have denoted 3 for alpha 1, 3 for alpha n. Okay. Then you do them together, and then you get a tree. And that's a bijection. That's very interesting. So, but here is assume that this is a monoform form, then it's clearly a big bijection.
No, also subtrees for the other alpha i's.
Yeah.
Sorry.
That's true. So for all subtrees, I have immediate subtrees. So if I have here n immediate subtrees. And this is the first function you would come up with when you want to associate ordinals to this. When you want to associate trees to ordinals. Every ordinal is canonically a tree. We have to know what is the number of nodes. So for this, we have to show what? The number of nodes at the alpha is what? It's 1 plus the number of alpha. So this is very important that there is a transition from trees to ordinals. And this equality here also explains why this norm function is a natural one. Because there's natural association between ordinals and trees. And the number of nodes in a finite tree is, of course, a natural notion. There's no discussion process. You can argue the norm function looks a bit artificial in the beginning, but you have this very precise connection. It's also The norm of alpha is actually the number of edges. Tree, but different story. So this is true by induction of alpha. Clearly is true for alpha 0. Because one node, the norm of 0. And what is the norm of T omega to the alpha 1 plus omega to the alpha n? What is the norm of the alpha 1? The number of what? The 3? Oh, is what? It's 1 for the root, plus the number of nodes in T alpha 1. Number of nodes in T alpha n. Now what? We apply induction. What is this? 1 plus. This one is T alpha 1, so it's 1 plus the norm of alpha 1 plus 1 plus the norm of alpha n by induction. Now we have n times 1. This is equal to 1 plus n plus norm of alpha 1 plus norm of alpha n, which is 1 plus the norm of alpha. So trivial verification. Okay. Now the magic comes. So we have here the sequence alpha I, and now we move it into a tree sequence T alpha. Right? Now we apply Friedman's theorem for this function here, and this function is basically chosen. That is nicely particular in this situation. So apply AP, and why is this possible? Because the number of nodes in T alpha I bounded by a square plus the I plus 1 3. Okay, and so what is going to happen? Then find I within J within to N such that the alpha I embeds in alpha J. Okay, that's fine. So we have structure. We have found in the descending sequence of ordinals, we have found two ones, I and means I and J, such that the ordinal alpha I, after moving into tree, embeds into ordinal alpha J. Now, what does this mean? Well, it means something strange. And we need to know a lemma. The lemma is following. If the alpha embeds into T beta, then alpha is less than beta. So this means alpha I is less than alpha J. What does this mean? This means the sequence of the alpha i's cannot be strictly decreasing, because at some moment, a later moment will become bigger. The only way that this is going to happen is where the alpha i's have a property they start over here, they become smaller, 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 and then it becomes constant. The only way that this is going to happen is that this alpha I is already hitting the bottom. So alpha I has to be 0. And then we are done. That's funny, right? So it goes. Now we have to find out this one. And that's how it goes. So first of all, assume alpha is bigger than 0. Because if alpha is 0, this conclusion is so assume alpha is a form next to alpha 1 plus alpha n. T of alpha is a form of alpha n. Okay. Now what do we know about beta? Well, the point is this 3T alpha has minimum 2 nodes. So even if alpha 1 is 0, would be here a node. So T alpha embedded into T beta, beta cannot be 0. That would be surprising. But then T beta would be a singleton tree. So what? I have now to draw a picture. Maybe I do it over here. Beta is of the form beta 1. Now alpha is alpha 1. And here is T beta, having the form T beta 1, T beta. First thing what we have to check is when we have here an embedding, then where does the root go? It could be that the root goes into one of those. If E alpha would embed into some beta I, or some I, then we can apply induction hypothesis. Then alpha is equal to beta I. This and beta. Voila. It's obvious. Now the only thing left is the root here goes into the root here. Then look at this node. This one has to go into one of the immediate subgroups. So the alpha 1 goes into some beta j. Okay, it's okay. Now what? Induction hypothesis. There is alpha 1 that's equal to beta j. Now what could happen? It could be if alpha 1 is smaller than beta j. Yeah, what is now going to happen? And then the whole omega alpha 1 plus omega to the alpha n is getting smaller than omega to the beta j is equal to beta by properties of being additive principle. Okay, what's going to happen is, if this is the case, then we are done. So now I'm running out of space, so it doesn't matter. Now comes some sort of inductive argument, namely, you can now assume that alpha 1 is equal by k. We use alpha 1, this somehow beta j. These are the same. Of alpha 1 of beta j. What does it mean? This tree here is the same tree as this one. Actually, there's a more to be said. And if beta j is smaller than beta 1, then by the same token, then alpha is smaller than beta. Right? This one smaller than this one, then alpha is 1. This is less than 3. What does this mean? We can actually assume alpha 1 is equal to 0. So this one moves into this one, but actually this one is the same as this. Not too bad. What the next step? Next step is we consider alpha 2. Alpha 2 moves into some beta k. For now, so here's T alpha 2. Has to be moved somewhere. This one goes to this one. Maybe this one goes to this one. Then we make the same argument. So in total, there's so we iterate, and so for all I less than n, find ji such as P alpha I basically embeds into T beta ji. And all beta j I or indices into I. So step by step, we move all the subtrees into different subtrees over here. At any moment, the tree in the left-hand side is moved into a tree into the right-hand side. The corresponding alpha I is less than equal to the beta ij. And then the point is, with this type of discussion, we can basically assume that we move those trees, the corresponding trees, to the left, to the right, in the order. So basically, this means if you work out n steps, finally you see the alpha 1 plus n. This is the beta 1 plus beta. Here you find the corresponding partner over there, and then you're done. Yeah.
It's also just possible to do it for alpha 1 subtree and then show that it's smaller and subtree. And then you just go to tree.
Yes, you can also do the argument by saying, look, just delete that one, this corresponding one, and by induction hypothesis, you apply it to the subtrees, yes. But you see some of the nature of things involved, that trees and immutability is closely related to ordinals and less than equal to relation. Okay, and so the lemma is shown. And then let's say alpha I is less equal to alpha j. This implies that alpha I is 0. It implies that all others are also 0. Or so the hierarchy is shown. Termination of the hierarchy is shown. Now you can ask yourself, well, this looks so beautiful. Is there more to say? Yes, there's something more to say. So the question is what to say best. So this is order. Now, if yes, less equal to is an extension of this array with a linear order, then storing is available. Now the question is why is this the case? Good. Assume, so we have here linear order. Assume that it's not well formed. Assume that this line strictly easy. This will take or what does it mean? This means one strictly smaller than now the sequence of trees. Cluster does makes this side in there such that I is embedded in Tj. Now this extends this ordering, so that means Ti is equal to Ti. But on the other side, we have here descending chain, and I is bigger than J. That's all possible. So interesting. So any linear extension of this tree ordering is a well order, and actually this is just the beginning of the theory. Namely, so we can consider what is called maximal order time. And what is this? This is the supremum taken from all order types of linear extensions. Then by magic, turns out maximum order type of T. And not only supremum, it's actually a maximum. Maximum in the sense there exists one linear extension realizing the maximum possible extension. And for Kruskal's theorem, the ordinal will be bigger than epsilon 0. So what we have seen is already we had a linear extension, tree ordering, namely this mapping alpha maps to T alpha induces a linear extension, but it's not maximally possible. So actually the maximal linear extension of the tree ordering is much bigger. But this doesn't matter for our discussion of PA. But if you have the maximal linear extension of the tree ordering, then actually the unprobability of Kruskal's theorem, the Friedman version, is actually not only unprobable in arithmetic, but all the theories which have strengths given by this maximal linear extension. So it is good to have seen it. And there's also a nice story with respect to Kruskal's theorem. There is one article by Ehrenfeucht, a famous one. In Algebra Universalis. And he proved he gave a solution to a long-standing open problem. The problem was the following. Namely, we consider a function class f consisting of it's a constant one function, identity function, and with f and g, and f, and then f plus g, f times g, and f and d are in f. And then we consider this ordered under eventual domination. And the question was whether this is well founded. And Ehrenfeucht said, well, look, this is well founded because we can use Kruskal's theorem by an argument like this. So these are, you can write terms for this, binary trees. And then he says, you apply Kruskal's theorem and the solution is done. The article is maybe 1 page long, maybe 2 pages, but one of the shortest papers which ever appeared in mathematics. And what he did is basically said, well, look, we apply Kruskal's theorem done. But this was the first convincing application of this type of tree embeddability to mathematical problems. So it's a very famous one. And there was a time where the article by Ehrenfeucht was on 1 page, and normally when you are Springer and go to a journal, it's after a paywall. So that article was not a problem because it was only on 1 page. So you saw the first page and that was everything, so to say. So I'm still dreaming of a publication just 1 page long, but that is okay. What's a moment for a break? Yeah. Okay. If there are questions, just let me know. Okay, just so we covered mainly the theory of Friedman's version of Kruskal's theorem. Now you would think that this is the end of the story, but actually it's not. So what we have seen is what was this critical constant? And I had find fr of I or what? Basically r times binary length I. And then I said if R is less than equal to C, then I does proof F13 R B R is bigger than C, then A does not. And this looks very sharp because you have one constant and but when you remember when we studied Ramsey theory or Hydra, we had always these functions which epsilon zero inverse showing up, or for Ackermann function or inverse Ackermann function showing up. In this result, you have just a constant. So there's no dynamics, but the point is you can study the function f alpha of I, which is p plus 1 divided by h alpha inverse of I. And now what is this for a function? Well, it's always bigger than this c, but this is an epsilon depending on I, and epsilon goes to 0. Then you can ask yourself, well, what alpha is fkt if alpha provable or not? And the final output is EA proves fkt if alpha is even if alpha is smaller than epsilon 0. Now there's a reason why I did not cover this, because you have seen already Kruspe was messy. This one is even more messy. Now, why is this messy? Because in our original presentation, we needed results about counting trees. Such that RTB of T is 9 by M, and T is on nodes. And then I quoted a result, namely that alpha M converges to alpha. And so what happened is when I proved my result in 2000, I went into this original article by Otter and I squeezed out this result. But later I found this reference by Go and Schmutz. And they proved much better results. And they proved actually not only convergence, but they also gave the rate of convergence. So much stronger results. But now for doing this result, we have to count the number of trees T, such as T as n hertz, and a specific general tree T M or Tk is not embeddable into T, and Tk in the tree the following form. It has k many direct successors, but at every node it has k many direct successors, and the height is k. And Gordeev and I, we calculated asymptotics for this. And this again, some alpha to the k to the n, and 3/2 times constant. And moreover, we needed effective rates of the convergence of this alpha k to alpha, long calculation. And if you have this type of information, then you are able to prove this one. But things become rather involved, and therefore I skip this. Now the probability part. So if alpha is smaller than epsilon, that PA does prove it. It's also complicated because the simple counting argument we did doesn't work. So you cannot just start with a k, defining m, and something is going to happen. What you have to do is you start with k, then you take the first tree, And then you count the number of trees where the first tree is not embeddable. It's a sort of messy enterprise. And this type of result has to be used to get this type of result. So this is just for information. For sure, this will not be part of the exam. But this is the real this is the final result in this context. But it's somehow so complicated that it's even difficult to communicate. Now, finally, we do a bit more recent stuff. So we have principal result, so-called Bolzano Weierstrass. Oh, that's easy. So this is Bolzano Weierstrass is basically this is n. This is the sequence in the unit interval. Real numbers. Then xn as converted into substitute. Okay, and how do you prove this? Take your interval. There lives an infinite sequence. And you divide this interval into two parts, and in one of the halves there's some infinite part left, and then you do bisection of intervals, and then this gives this leads to a construction of a real number, and then you can choose the subsequence converging to this point defined by these interval bisections. And there's also monotone convergence. Every monotone sequence is the limit. And what is interesting with these statements is they have some proof strength. So when you study results from reverse mathematics, there's some complexity involved. But we don't go too much into this. We do the trick by Harvey Friedman, namely, we make an arithmetical statement out of it. So Friedman's version of Bolzano Weierstrass, let's take the function f, the following. Again, for all k, there's an m. The m can be big, such that for all 0 to m, we find k numbers. We want k. Let's say k is at least such that for all L less than k minus 2, here's the distance of xk L plus 2 minus xk L plus 1 is bounded by f of k. Now, first question is f is the function with numbers include real numbers, just fictional polygons. But for the rest, it doesn't matter. Now, this is sort of difficult to understand. So, if the two statements. So Harvey Friedman proved submitted this to a news email listing email list and just claimed this is true. And then he gave a proof, and he was applying a theorem by Tifanov, namely that the product of compact spaces is compact. So it's somehow a difficult result in topology. That's fine. And now what we want to discuss today is the question, what can we say about when we have given certain functions f? When is it provable and when it's unprovable? And the point is, one can show that these m's, so let's say this function f is 1 divided by f of L could be, for example, 1 divided by L. Then this m is an Ackermannian function. If f of L is log of L divided by L, one can go along here with an exponential function. The obvious question is what's going to happen in between. And this was interesting. So, question by Friedman was, what happens for functions f of I is 1 divided by I, or f of I is 1 divided by I times log of I. And so this is what I did last year. I answered this question, and I will share my answer because it's actually doable. But before doing so, I studied all the monotone version of Bolzano Weierstrass. If the sequence is increasing, then this is very one, k. That is for all L is equal to k minus 2. We these distances formed by f of k. And so when I did this, I proved the following. Namely, theorem. F of I is what? 1 divided by I, logarithm of I, 1 to the epsilon. Then M, the function of K, is Ackermannian. So M of K, so M, if I take this as the smallest possible one, that's a number depending on K. And if f of I is 1 divided by I of I, then M of K is bounded by a double exponential function. Therefore, it is low complexity. And this is for the monosphere. So this I achieved quite early. Then I spent basically a month on figuring out what this result has to do with the original question, right? But this is somehow easy, and therefore I will show it to you. Maybe you will like it, maybe you don't. So what? Okay. Done by time. And let J begin. What can we do with M? The double exponential, so let's try. M is very equal to the. Okay. Maybe we have to adjust it a bit, but now what? Now we have to prove. So we have M. Now we have given the sequence. And assume that it is a monotone sequence. Yeah. Now we have to do something. But we have not the slightest idea what to do, right? So it's just so we have now to find these numbers. Okay, so what's the picture? The picture is as follows. Here's a unit level. And now we start some process, not the bisection process, but the new process. So let us consider an interval. I1 is the interval, the left endpoint is 0, and the right endpoint is the 1 divided by f of k. Here, I1. Now there are two options. Case 1, if now the first k elements are in this interval, that's fine. Then I have k elements. Then I say my indices here, just the numbers which I've seen over there, right? Let's say L is k. And then what? It's k L plus 2 minus kn. Okay, we say what's the difference? Bounded by 1 divided by f of k. Right? No discussion. But k is bigger than all the ks. So KL is strictly smaller than k, so that's it. What does it mean? This means we start here, and when we have packed the elements too closely together, I'm done in step number 1. So it means one element sits over here. So I assume that x I0 is bigger than okay. So from I0 Now consider. Yeah.
Sorry, I'm not. I'm a bit confused. So you need to have that it's smaller than f of kl, and
Yeah.
we have written 1 over f of kl.
Then I made a mistake.
Shouldn't we change the interval or
No.
What
which one is? Take here. F of k. Okay, right. Those In some of my papers, I use F, and sometimes I use the reciprocal.
Then it's not obvious that f of KL is larger than f of KL.
Well, KL is smaller than. So these are numbers between 0 and k minus 1.
Yes.
Yeah. Oh, sorry. So that's.
Yeah.
Okay. But you are perfectly sensible. I was. But this is sort of. You can kind of this. You could come up with this argument in Bachelor 1, right? Nothing has happened. Now you see here I0. So we assume that I0 is x I0 is already here. Now we consider the element x k plus k minus 1. So the next k elements in the sequence. They are to the right of this point. I have to say what is the interval. Now the interval I2 is designed in the following way. I2 has the right left endpoint of A, and the right endpoint is f of k plus f of k plus k. Now there are two cases. It could be that all these elements are in this interval. Well, if this is going to happen, then we are again done. Right? So if k is k plus k minus 1, then what? Now for my indices, I take those numbers. So KL, I take it as x k plus 1. Now, what can I say? The distance between x k plus 2 and x k plus 1 is bounded by, how long is this interval? I take the rightmost point and subtract the left one. Okay, f3 plus k. Smaller than k. That's good. So it means if I have here elements, then there will be some I1 leaving the interval. Now you would think, what is the next interval? I3. I3 is we take and on the right we take f of k plus f of k plus k plus f of k plus k. And now what is the argument? Well, now we consider the elements x k plus k, x k plus k plus k minus 1. And then you see what we can do. We can iterate the construction, right? If all these elements find this interval, then you're done. Otherwise, there will be a point to the right. So here's then somehow actually one point that we want. Now, okay. The question is what's going to happen? The point is, at some moment, one of these trivial cases will show up. Now assume that always jump to the next interval. Well, here's a new interval, new interval. Now comes the trick. What is the trick? The trick is that these intervals will at some moment cover the unit interval. So at some moment, it is no longer possible to come up with a new subinterval. Now the question is, why is this the case? Well, take a sum. F1. Now we have here m many elements. The number of intervals is maybe m divided by k. And what do we sum is basically, let us sum the length of this interval plus the length of it. So what is going to happen? We sum over 1 divided by k plus n log k plus n. Right? That's the what?
I did not k log k times I. Or because we are
Let's see. You are maybe right. I have to check. K times I times logarithm of k times. Now it's better? Yeah. Okay. But you see, I was going on, I just sum the length of the intervals. Now, this is basically as good as the sums and integrals somehow match up, so to say. And now we take log of k times x, and we take the derivative of it. What's going to happen? We get what? 1 divided by log kx times, and derivative of this one, 1 divided by kx times k. Okay, so it's basically as good as like in the primitive. Maybe 0 is maybe not good because then I divide to 0. Okay. And this is basically what? Oh, it's primitive. I'm wrong here. I have to plug in here what? So if I have here 1 divided by k, this disappears. So I have to take the primitive of this one, this term, 1 divided by k log of x. And now you plug it in and over k. So it's 1 divided by k log of k times divided by k. Okay, what do we get? We get the log of m, and m is to the k. So we get 1. Now, what does this mean? When you make m a bit bigger, you get a number bigger than 1. So if you take here m squared, for example, then you get here what? You get here not m, but something like k squared divided by k squared. By squared divided by k bigger than 1. So you see, by magic, some moment out of the blue, you get an estimate, and then the result comes out. And so this is a somehow beautiful proof. Just you have a problem in combinatorics, you put your stuff together, and at some moment you do an estimate, and that's it. And now what you learn here is, of course, it doesn't depend on these functions. The only thing is, what is needed is that these sums over fki, I goes from 1 to n. They have to be set up in a way that they are bigger than 1. So then you can plug in here more functions, right? Basically, you can plug in all functions that the sums are divergent. And of course, it depends a bit on how they are divergent, so to say. But when you take, for example, f of I, 1 divided by I, f of I, log of I, then this argument with the derivative shows you get log of log of log, so you get a triple exponential. So if you have here log d of y, then you need power of exponentials of d plus 1, and you're done. So that's nice, right? Now, okay. Next question is what's going to happen when the sums are converging? When the sums are converging, you can make up this argument, but then the intervals, they don't fill the unit interval, and so there's no conclusion which you can make. You can only make a conclusion when you cover the full unit interval, and for this you need the divergence of these sums. Okay, so this was a beautiful argument, but then I was stuck for a long time because this argument clearly requires that we are going from the left to the right in the unit interval, right? You do here some stuff, and then you go to the right. And then always to the right. But when you have a non-monotone sequence, the points can fluctuate. You can jump from the left to the right, from right to the left. And I got crazy by this. So what I tried to do is, I tried for a long time to show that the phase transition for this function will lead to an Ackermannian function. So what I started to do is I started with some interval and I tried to model a fractal or whatsoever with distributing points uniformly distributed about the unit interval, but I never succeeded. And the reason is that basically this bound also works for the non-mode conversion. And that was a big surprise. So I was for half a year trying to prove a wrong result. And you can imagine that you have a hard time because it doesn't work out. Now I will show the solution for Friedman's problem. And don't worry, it will be not more complicated than the solution here. Just sort of yeah, let's say a k-fold iteration of the case, the monotone case. Okay. Yeah, now it becomes a bit ugly. So again, we have f of I is 1 divided by, well, I make the situation simpler, but we don't want to discuss now, let's say, problems from calculus. If I have I log I, the calculation is slightly more complicated, but it will just be the same. To simplify matters, I just go to this function. And m, so let k be given. And m is basically some partial exponential function. Maybe a bit more, maybe times 5. But that's not so important. Now consider these elements. We zoom in, look at x0. Where can x0 be located? Can be somewhere here. Or x0 can be located over here. Or it can be located over here. Now, I collected these 3 cases, the following case distinction. So if x0 is in the leftmost interval, then my starting interval is 0 and 100. So here is the interval. Now, but since it is a non-monotone sequence, it could be that x0 is over here. If x0 is in the last interval, then but the length of the interval is k, right? Okay. Then I0 is this interval. And the remaining cases, so that would be the case here, or x0 in the middle. What can you do when you're in the middle? You take an interval around x0. The length of the interval is k, 1 over k, and it's you take a ball around x0 with diameter 1 divided by 2k. Otherwise, pi0 is what? It's a ball around x0 with radius k. I take a closed interval. Okay. Now we do the trick from before. If x0 is k minus 1 and I0, then you're done. Okay. Because if k elements are in an interval densely packed of diameter 1 over k, I can do the estimate as before. Okay, so that's nice. Therefore, we can assume that some of these elements will be outside. They use disjoint, so assume some I0 is not in I0. So what we do is now we take the unit interval and take out this interval. Then the remainder is the union of two closed intervals, or maybe two open intervals, but the endpoints are not important for our discussion. So let's say for simplicity, we have the situation here's J0, this J1. To assume that xi0 is in convex number. The other case is symmetrical. Now we consider this J0 as a new unit interval. So we look where is this xi0? Either it's to the left, or it's to the right, or it's somewhere in the middle. Yeah.
So we are wanting to do the same thing for non-monotone.
Yes.
Right. But so I was wondering, how does the statement then read off, since we don't really
The statement is this one, where we drop monotonicity, just arbitrary sequences. For any sequence long enough in the unit interval, we find a subsequence, the k terms are close together.
Yeah, okay, yeah. So that, yeah, we don't need necessarily.
Yeah, and now the point is that they can these elements can jump freely back and forth. And
so we can always assume that there are enough elements in one of the, yeah.
So the point is, if I take the first interval around x0, and the first k elements are in this interval, then I'm fine. But of course, the interesting case is that one is outside. Now I have to define what is the next one. So what we are going to define is an interval I index k. Now what we do is we look as follows. Namely, whatever we do. First, you can check well, we will have an interval diameter ik should be not 1 over k, but it could be 1 divided by 2. Okay, so we look when we have this interval from here to here, diameter 1 divided by 2k. And if xi0 is here, then we take it. So if xi0 is in the interval 0 to 1 divided by 2k, then k is more. The other case is xi0 is more to the right. If xi0 is in an interval, and now it's a bit difficult to say, let's say this is A. So in the interval of the form, I have the rightmost endpoint A, and then it's A minus 1 divided by 2. If I can squeeze it somewhere to the right, I'll take that. So it's sort of greedy algorithm. So when it's far to the left, it takes a canonical interval of this length to the left. When xi0 is far to the right, I take canonically the interval which matches precisely with this left right endpoint, and this will form ik. Now the third case is xi0 somewhere sits in the middle. Then I do the ball around xi0 of the length 1 divided by 2k. So otherwise, ik is what? It's a ball around xi0 of length 1 divided by radius 1 divided by 4k. It would be something like this. Okay, that's nice. Now there are different cases. Namely, the question is it possible? No, the next case is, of course, I check whether the elements, if it's k plus k minus 1 are in ik, then we are done. Right, by the usual argument. Therefore, some element has to be outside. Now the point is, if it's always possible to choose points outside, and I have disjoint or intervals which are basically disjoint, and the total length will be the sum which we have seen over here. So this means you cannot have the situation that I always choose new xi0s which are sitting in new intervals. At some moment they will be overlap. That's normally the point where you would give up in your construction, because then things become messy. Well, what could also happen is the following, namely this interval S0 could already be here. It could be that xi0 is already here. In this case, here's the situation that the new interval ik has a non-intersection with the previous interval. How does this problem occurs? No, anyway, it doesn't matter. So if ik intersected with i0 as then the open part empty, then ik is in one category up, and otherwise it is in category. So what we do is we consider these intervals, and either they intersect with previous intervals or they don't. When they intersect with previous intervals, I say they're in category up, and when they are completely new, they're in category down. Now, it cannot always be in category down, as we already have seen, because the sum of the length is divergent, so this is not possible. So there will be intervals in the category up. But now look at the following situation. So here we have some previous intervals. Oh, sorry. This was just a construction of I0 and IK. This will now be iterated. So we have here the situation. Always try to find new points. The xi's are always new, but it could be that the intervals here are intersecting. Now, when they are intersecting, there are certain reasons for this. Namely, in this construction, we first try to fill up from the left, then from the right, and then in the middle. Now, if one interval somehow intersecting an old one, so if here is an xi0, and if this, maybe this was, maybe we had the situation that here was I0, here is xi0, and I do the interval over here. Then this interval intersects with this one. But now the next one, xi0, xi1, is chosen in an interval which has new free space. And when it intersects with another one, this interval around xi0, xi1 will never intersect this interval because there's another interval in between, and the length of this interval is longer than the length of this interval because the intervals become shorter and shorter. So what does this mean? I have intervals in the upper category. I have intervals in the lower category.
Like, could you just it's going a bit quick for me, I sound.
Yeah.
So how the labeling of the interval? So because now you have some order on the vector, but that's not.
Yes. So okay, still some time left. So what we do is first we take I0. There's no constraint, and so we put this in the down category. Then the next step is this is xi0. It's not in I0. So it's somewhere to the left or to the right. And we have just discussed the case here is I0. Let's say this one. And xi0 is over here. Now it could be if you have to choose this leftmost construction, and you have to put an interval over here of length 1 divided by 2k, but it could intersect with this one. Okay, so in that case, I give this interval label green. Okay, and then I look for xi1. xi1 sits in a new place, it has not been used before. Therefore, if I put an interval around this, it can intersect with one of the previous ones, but for sure not with the green one, because there's another one in between. And first we fill up from the left, and then from the right, and then in the middle. So if here is an interval intersecting previous stuff, it is not possible to intersect with the green one. So what does this mean? It means the following. If it's always possible to choose new xi0 in free spaces, then we select intervals either in the down category where the points are new and where the intervals are completely disjoint from the previous ones. Or we choose points where the intervals intersect non-trivially with the previous ones, but they are organized in a way that the ones in this category don't intersect. And then the point is the sum of the length of this one plus the sum of the length of this one forms also a divergent sequence. What does this mean? This means the following. So we have our construction. We have here x0, then here's an xi0. Then comes xk plus I1. Then comes xk plus k plus I2. And the point is, we want to have them new, but if they always would be new, then the intervals produced are in those two categories. And at some moment, the space is taken over. So what is the upshot? The upshot is, at some moment, if you go for a new one, stepping out of a small interval, it has to re-enter an old interval. So there will be some moment in time, let's say it's entering this interval, there's some x k times p plus ip enters such an interval. That looks like a complete disaster because we want to have disjointness to make our counting work. But now what's going to happen is we look at this interval and only stay in this interval and consider this as somehow a new unit interval. So if a point of this type enters a previous interval, let's say it's over here, then we do either left construction or right construction or an intermediate construction inside this one. And you can do inside this one because the length of the new interval is shorter than this one. And then we continue. So either we look for the k times p plus 1, this k times p plus 1, k times p plus k minus 1. We look for the next one. We leave this small interval. And there are two cases. Either we leave the whole interval completely, going over here, or we stay in this interval and then we make a new interval over here. What does this mean? We make up, so here's level 0. Once we entered an old interval, the intervals will get to level 1. And then you can imagine that in level 1, so inside this interval, you make a new hierarchy of intervals. And if you have only level 1 and level 0 intervals, the sum of all of them would also be divergent. So actually, if you work long enough, what you obtain is you get a sequence of intervals which are sitting in each other with k many points waiting over here. There's here a point, there's here a point, there's here a point, but the distance between all the points is bounded by the length of the, and then we are done. But you see, this type of argument is extremely messy to write up, but it's even more difficult to find it because it looks completely hopeless. You start, you do your easy construction, and you see, there's the first problem when intervals overlap. And then, okay, I came up with this idea, but then the problem is if you re-enter with your new xi0 previous interval, then you basically are losing your situation. And then just having the idea that's not killing the whole argument, you can just continue inside your old stuff in a new level, so to say, gives you the option of having a k times nesting, and the k times nesting of intervals leads to points which are closely together, and that's basically finishing the arguments. So basically, I would say EPC, and then you can work out the details by yourself. But you see, this argument is not obvious, and that's all the reason why Harvey was not able to find it. Okay, now we have 5 minutes left. It's maybe not worth to do much more. I can put the posting by Harvey on the Fora sites, and you can see the original posting with the proof, the truth of the statement using compactness, and it's somewhat interesting. And yeah, okay. I hope that you enjoyed this. There's something which I want to, its final end, to say about, we have seen the Heider battle stuff, but there's also the slowly well-organized. Yeah, and just gain the result. Following certain properties K, there's an M, such that all systems are oneness. I with an M, such that alpha I is equal to M. So it speaks about the miniaturization of the principle that the ordinals in E are not strictly decreasing. And why is this interesting? Because one can do the phase transition, and to do the phase transition, you need stuff. You need bounds on the number of elements. Of this form. And of this form. And the question is how to obtain this, right? So this is called, let's say, C omega omega the n. This is totally, maybe I showed it already. It's I square root of 2 over 3 is n divided by 4 times square root of 3 times n. Now, how to prove that one? The point is, it has to do with number theory. And so the sum over C omega omega to the n, that's the presentation as product 1 divided by 1 minus whatever this makes sense, it's clear, but it makes sense, and really it goes back to Hari and Ramanujan, and they squeezed out this one from this presentation. Now, you have to know a bit about these generating functions, but if you go this a bit more, C omega to the omega to the omega of m to the n, and basically the product of this form. Here we have C omega to the omega I plus 1. So you get some sort of power series. And by magic, you can do something with the power series, and you can get off information of this. But to understand this, basically, you have to know that every ordinal alpha is polynomial form. the norm function is additive, and basically alpha can be written as a multiset of orders of smaller height. And this gives rise to such representations. And when you want to see how to get this information out of this one, before I've written, I put paper by Petro Gradsky, and he shows how to do this. And the paper itself is about Lie algebras and whatsoever. But as a side product, he proved asymptotics for certain formulas. The counting comes, and the counting gives precise bounds for the phase transition for the statement. But I didn't cover it. But I just want to show, if you like this type of number theory, you can see it. And if you want to understand why this one leads to this type of generating functions, so sums are going into products, there's a book by Stan Boris. And one of the introductory chapters explains precisely if you do the counting of multisets, how this transfers into these infinite products. But it's also not part of the exam, it's just to fill the last 5 minutes. Okay.